Welcome to SGIT Meister. Today we're going to explain quantum computing. Watch till the end for better understanding. Like, share, comment, and subscribe.
Much of the current market noise surrounding the field of quantum computing treats it as a trending software optimization. In reality, quantum hardware relies on physical laws that are inaccessible to silicon transistors. Standard classical computing relies on deterministic bits that evaluate data in a strict linear sequence, reading either a 0 or a 1. We are deconstructing this architecture from the individual physical unit up to its integration into real-world enterprise environments. Navigating this new hardware requires a complete transition from classical deterministic logic to calculations based on probabilistic possibilities. The bedrock of this framework is the quantum bit, or qubit. This diagram compares a classical bit, which functions like a 2D toggle switch, to a qubit, which maps data to various internal coordinates within a 3D sphere. This spatial geometry enables superposition, allowing the qubit to hold multiple states simultaneously. This allows a quantum system to represent and navigate massive possibility spaces all at once, rather than evaluating one path at a time. Superposition is the mechanism that allows a single quantum unit to process a larger volume of information than classical hardware. A single qubit is limited. To form a computational network, these multi-state units must be connected. This model demonstrates entanglement. When qubits are linked, the state of one unit triggers an instant reaction in the other, regardless of the distance between them. This interconnected web drives processing power up exponentially with each added qubit. However, because the system processes all possibilities at once, extracting a single deterministic answer requires a specific filtering mechanism. Extraction is achieved through interference. As shown here, the system treats data as overlapping waves. Aligned peaks amplify each other, while peaks meeting troughs cancel out. The system uses this interference to mathematically amplify the probability of the correct outcome, canceling out incorrect ones. This orchestration ensures that incorrect answers destroy each other, leaving only the optimized solution to be read by the user. Moving from theoretical math to physical execution requires highly specific and fragile engineering. These machines rely on dense bundles of gold and silver wiring within dilution refrigerators to maintain control over the qubits. Operation requires temperatures fractions of a degree above absolute zero, an environment colder than deep space, to keep the system stable. Minor temperature fluctuations or background radiation cause high error rates. This explains why the IBM Q System 1 is housed behind thick environmental glass. The infrastructure is currently expensive and limited to specialized laboratory environments. Because of the delicacy required to maintain superposition, quantum computers function as massive industrial installations rather than consumer-grade devices. Enterprise value is found in multivariable optimization problems that create bottlenecks for classical systems. In cybersecurity, quantum processors can rapidly factor the massive prime numbers that form the basis of current encryption. In healthcare, they allow for the simulation of complex molecular structures, which is critical for drug discovery. These systems optimize global supply chains, model financial risks, and generate high-fidelity weather forecasts. The immediate utility of this technology is solving the specific simulation and optimization tasks that classical supercomputers cannot process. It is a misconception that quantum processing units, or QPUs, will replace standard classical CPUs. The future IT stack is a hybrid model. As shown here, a classical server rack identifies a specialized optimization task and routes it to the cryogenic QPU. The QPU functions as a specialized coprocessor, working alongside existing infrastructure rather than replacing it. This establishes quantum hardware as an auxiliary optimization engine for the most complex problems in existence. Moving into this space requires a specific technical skill stack. Foundations in linear algebra and probability are required to understand and structure quantum logic. Proficiency in Python is the standard starting language for classical quantum integration. Mastering specialized frameworks like Qiskit and Cirq is necessary to write the actual hybrid circuits. This technical synthesis provides the tools needed to deploy production-ready code on physical quantum hardware.